All right, welcome everyone to our sixth lesson of the semester. So last time we saw that we can exploit Pythagorean identities to turn integrals that didn't have seemingly anything to do with trig into trig integrals, which we now know how to do. And it was kind of a long process, but sometimes it's kind of the only method we have for doing some integrals. Now, last time we were able to do integrals that looked, I don't know, maybe something like this. This one we should know how to do. Pop quiz, does anyone remember which trig function we should use if we have x squared plus a number squared? Very good. That's right. We're going to use tangent. And in particular, we would use 3 tangent because it's the square root of this number right here. All right, so we know how to do ones like this, but what happens if we have something even just a little bit different? Like what if we have 9 plus x squared? So we could try to do the substitution again, but we won't quite have a Pythagorean identity underneath this square root because of this annoying extra x right here. So does that mean we're doomed? Does this one a frowny face? Are we stuck with this one? Well, it turns out the answer is no. It turns out that we could still do trig sub with functions, even if they look like this, using an algebra technique that you may have learned long ago. So anyways, that's kind of what we're going to be doing for today's lesson. We're going to practice more trig sub, and we're going to see how to do it in some different situations. We're doing trig sub part 2. Okay, so what we're going to do first before we do any kind of calculus or integration is we're actually going to review an algebra technique. I don't know if you guys remember this or not. I certainly didn't when I was taking Calc 2. This technique is called completing the square. And this technique allows us to turn things that look like this into things that look like this right here. So let's go ahead and see an example of this in action. So let's see an example here. So I want to complete the square with this polynomial, 2x squared minus 12x minus 14. I want to complete the square right here. All right, and if you've forgotten how to do this, or maybe you even never even learned how to do this, don't worry. We're going to go over the whole thing, and we're also going to practice this too. So we will have some opportunity for practice here. All right, so the first thing I like to do when I'm completing the square is I factor out anything that's in front of my x squared term. So the first thing I'm going to do here is I'm going to write this as 2 times x squared minus 6x plus 7. And I'm going to focus all of my efforts inside this parenthesis here. You technically don't need to do this to complete the square, but it's a lot easier if you do it this way. All right, now what I'm going to do is I'm going to look for, oh yeah, what's up?
Is it minus 14?
Oh, you're right, thank you. It is minus 14. All right, yeah. that would screw us up later because this example ends up being part of something else. All right. Anyways, so what we're going to do now is we're going to look for what I like to call the magic number for completing the square. And that magic number is going to be b over 2 squared, where by b, I mean the number that's in front of the x term right here. Okay, so what's our magic number for this problem? Well, we have negative 6 over 2 squared. That's going to be 9. That's what we're going to be having here. All right, so what are we going to do with the number 9? I mean, it's a nice number, but what does it mean for us? Well, we're going to add and subtract it right next to our negative 6x. So we're going to add 9 and subtract 9, and we have minus 7. And we're definitely allowed to do this because 9 minus 9 is 0. And we're always allowed to add 0 whenever we want. It doesn't feel very meaningful, but we can do it whenever we like. Now, the reason why we did this, the reason why this number is so special is if we look at the first 3 terms, if we write it in this way, we should be able to factor these. So if we do that, let's see, do we have any factor fiends out there? Does anyone know what this is going to factor into? What is this going to be? X minus 3 squared, absolutely. x minus 3 squared. That's what these three are going to turn into. Now, meanwhile, we have the -9 and the -7 left over, right? So if we combine those together, then we end up getting -16. And there we go. So we've been able to complete the square. So we turned something that had originally a middle term right here, and we were able to turn it into something where we have a square here, and then a constant right there. And then maybe if we wanted to do a trig sub with this problem, then we could have this equal the trig function, and we'd be good to go. So that's what I mean. This is how it's going to be useful, because we can get rid of this middle term, and we can turn this into something we could do trig sub on. So this is completing the square. And if you like, you could put back in the 2 if you want. Although usually I think I'm going to say that we prefer it this way, but you could also, if you really like to, you could also write it like this. Not wrong to do this. All right, so now that we've done that, now that we had a review, we factor out the thing in front of x squared, we add the magic number, we factor, and then that's it. So why don't you guys practice one? And this is going to be our first Canvas practice problem of the day. So I want you guys to complete the square with 3 minus 2x minus x squared. So why don't you go ahead and draw this here? Or draw this. I was reading Joshua's comment. Why don't you go ahead and complete the square here? Where did I get the constant from? You mean the -16? Well, when I added the 9, I also had to subtract the 9, and we already had a -7 in this problem. So these leftovers here, these combine to be -16. Now, one suggestion for this one, there technically is something in front of the x squared. It's a negative. And I would subtract, I would factor out the negative before you do anything else. You always add first, then subtract? Yes, because you will always end up having addition for your last term here for the factoring. So it's always adding and then you subtract it. We got some disagreeing answers here. Oh, yeah, it depends on if you put the negative back in there. Negatives are kind of an exception. So I said, oh, let's not put the constant back in there. If it's a negative, you could go ahead and put that back in there. That would actually be okay. I'm just talking about like a positive. Give you guys another few seconds here to give this a try, and then we'll go over it. All right. Let's go ahead and give this a try. So I noticed that I have something in front of my x squared here. It's a negative. So I'm going to move the negative out. That's going to give me x squared plus 2x minus 3. I factor all of that out here. All right. So then what I'm going to do is I see, okay, I have a 2x here. 2 over 2 squared is 1. So that's going to alert me to the fact that I should add 1 and subtract 1 inside here. All right. Now, if I've done this correctly, if I pick my magic number in the right way, these first 3 guys right here, these should factor. And they will factor into x plus 1 quantity squared. Then these 2 leftovers will combine into a constant, -4. And then finally, oh yeah, if you do want the answer in Canvas, you should redistribute it. So I guess that's important. So if we put the negative back in, then it's going to be 4 minus x plus 1 squared right here. There we go. So we were able to take something that had this annoying middle term, which prevents us from using trig sub, and we were able to turn into something that might be a little bit more easy to use trig sub. Okay, so that was kind of an algebra review, or maybe a little algebra lesson if you haven't seen this before right here. So now we're going to go ahead and get back to calculus here. So my second example is actually going to make use of what we just did. So let's try to do the integral of theta divided by the square root of 3 minus 2 theta minus theta squared, d theta. All right. So let's see here. So how are we supposed to do this? Well, the bottom almost looks like it could be completing, or sorry, not completing the square, a trig sub. We just have 3 minus theta squared, but unfortunately, this 2 theta is in the way. But now we can use our new technology of completing the square to make this into something a bit more favorable. And if you guys notice, this is literally the same polynomial that we just worked with, right? Except instead of x's, they have thetas. So that means if we complete the square, we already know how to do that. So if we complete the square, this integral is the same as theta divided by the square root of 4 minus theta plus 1 squared. All right. Yeah, I try to abbreviate as much stuff as possible, so I will write it like this. All right. So now that we have it written like this, now this is something where we could use completing the square. So this completing the square is of the form a squared minus x squared. So do you guys remember which trig function will work well with that? We have a number squared minus a variable squared. Which one did we use for that last time? That's right. We're going to use sine here. So our x is going to be a sine of theta. Okay, now this is actually a little bit awkward, right? Because usually theta is the variable that we switch into, but we already are using theta for this problem. So this is one of the rare cases where we're not going to use trig sub with the variable theta. Usually, as is tradition in math and often physics too, if you've already used theta and you need to use an angle again, a backup theta is going to be phi, which is just you can draw with a circle with a line through it. So what I'm going to do here, I take whatever my variable thing is that I'm squaring, which is theta plus 1. That's effectively my x. My a is going to be 2, because that's the square root of this. And then my trig function is sine, but I can't use theta because that's my current variable, so I'm going to use phi for this right here. All right. So where can I find all these substitutions? Let's write them out again, because yeah, we should remember these here. So a squared minus x squared. This is going to be a sine of theta is x. X squared minus a squared is a secant of theta. And then a squared plus x squared, that's a tangent of theta. So these are going to be the 3 different substitutions we have. And remember, we should treat the x a little bit more loosely than just an x. Like that's what we did here. The x, the way to think about that is whatever involves the variable. So this time, rather than just having a theta squared, we have theta plus 1 squared. But whatever the thing involving the variable is being squared, that's what we're going to set equal to our trig function. So even though it's not just a theta squared, it's a theta plus 1 squared, we're going to use theta plus 1 for our substitution. And we'll see a few more examples kind of like this later, so we'll get used to it. All right, so now we have our substitution here, right? This is going to be our substitution. So let's go ahead and compute the differential. So if I do the derivative of theta plus 1, that's just going to be 1 d theta. And then the derivative of 2 sine of phi is 2 cosine of phi d phi. Which one is the actual theta? I don't know what you mean by actual theta, I guess, but theta for this problem is our original, and phi is usually what we would use for our angle. This would usually be theta, but we already used that. So I'm using phi as my backup theta right here. All right, so now that I know what my differential is, I can go ahead and plug everything into my integral. All right, so I have theta up here. Now, the thing is that I know theta plus 1 is 2 sine of phi. So what's theta going to equal? What am I going to write in my numerator up here? If I have just theta. Theta plus 1 is 2 sine of phi. Then that's right. We're going to have 2 sine of phi minus 1 right here. Why are we using phi? Because normally we would use theta as our new variable. But in this problem, we have theta as our old variable. So we need something different to be our new variable. And whenever I want to use theta, but I can't, I use phi. You guys don't have to do that. You can use t. You could even use x, because we don't have x anywhere else in this problem. But I don't know. Phi is traditional if you want another angle variable. That'd be more along the lines of what you would see written in like a book or something. Or a paper. All right. So we have a d theta right here, and then d theta is 2 cosine of phi. And then on the bottom, this is where we have our Pythagorean business going on. We have 4 minus theta plus 1 squared. So theta plus 1 squared is 4 sine squared of phi right here. All right. So now we've converted our integral into phi's. And now usually after this, then we want to use a Pythagorean identity to make things simpler. Let me ask you guys this. What is the inside of the square root going to turn into? What's that going to be? That's right. It's going to be 4 cosine squared. Because remember, this is the Pythagorean identity. If we have a squared minus a squared sine squared of something, then that's going to end up being a squared cosine squared of whatever that thing is. And in this case, the thing is phi. So we have 2 sine of phi minus 1. We have this 2 cosine of phi hanging out here. And then we have the square root of 4 cosine squared of phi. Okay. Now, as always, as most of the time, we can end up canceling out the square root with what we have down here. So this will go away, this will go away, and this will turn into a 2. So all in all, we're going to have 2 cosine of phi down here. Now, what's the nice thing about that? What's going to happen with 2 cosine of phi down here when we do the square root? That's right, it's going to cancel because remember, we have this 2 cosine of phi up here that we got from this differential. By the way, I think someone asked earlier why this is what it is. I just took the derivative of both sides of my substitution. That's always how we get our differentials. The derivative of theta plus 1 is just 1, and then I have d theta. And the derivative of this is 2 cosine of phi, and then I have d phi. Why did I cancel out the square root? It canceled with the square and turned this 4 into a 2. Yeah, what's going on in the denominator? So this is the Pythagorean identity, right? This is the main reason why we do these substitutions, is so we can get something like this. Whenever I have a number squared minus a number squared times sine squared, if I subtract those, I get a number squared times cosine squared. That's how I get from here to here. I got this 4 cosine squared. Then I did the square root. I guess I shouldn't skip this step here. Let me write this out again. So I do the square root of 4 cosine squared. And I end up getting the square root of 4 is 2. Square root of cosine squared is just cosine right there. All right, and then I see I have the same thing on the top and bottom. So I'm going to cancel those out. And now all I'm doing is just, I'm going to do the integral of 2 sine of phi minus 1. And thankfully, we don't even need to do any of the new stuff we learned. This is actually just a Calc 1 integral. So if I do the integral of 2 sine of phi minus 1, I get negative 2 cosine of phi, because remember, we get an extra negative sign when it's sine, minus phi plus c. All right, so now we've done the integral, and now we're going to have to convert back into thetas, which remember, theta was our original variable here. All right, so let's see. So the substitution we did originally was theta plus 1 is 2 sine of phi, like this. All right, so first of all, we need to get what cosine is. And do you guys remember how we got different trig functions from the one we substituted in? What was the little method that we did to finish these guys off? The triangle, that's right. We set up a right triangle, and I also saw Pythagoras in here. We used the Pythagorean theorem, that's right. So first of all, I need to make my ratio so I could build my triangle. I'm going to divide by 2. So I have theta plus 1 over 2 is sine of phi. And sine, as we know, is going to be opposite over hypotenuse. So as I draw my triangle here, here's my angle phi, and my opposite side is theta plus 1. My hypotenuse is 2. Okay, so if my opposite side is this, my hypotenuse is 2, then we could use the Pythagorean theorem to get the adjacent side. So a squared plus theta plus 1 squared is 2 squared, or 4. This is the Pythagorean theorem. So if I subtract this, and then I take a square root, I find out that my adjacent side is root 4 minus theta plus 1 squared. And where have we seen that before? Where did this show up? We've actually seen this before. Yeah, Bianca has it. We saw it in the beginning. So if we go all the way back to the beginning of our problem, well, not quite the beginning, after we completed the square, we saw that our original integral that we were doing is this right here. And remember, I said a good way to check your work is that if we see this appear in our triangle calculation, it means we're on the right track. So that's a good sign right here. Anyways, now that we have our adjacent side, let's figure out what cosine is. We have negative 2. Now cosine is going to be adjacent over hypotenuse. So we use our new adjacent side, and then we divide by the hypotenuse, which is 2. And conveniently, those will cancel out. Now finally, we need to get what phi is going to be. Do you guys know what phi is going to be? How do we figure that out? Just phi on its own. We're going to use the inverse functions, and we're going to use arcsine specifically. That's right. So back up here, I have written theta plus 1 over 2 is sine of phi. All right. Well, if I want to undo a sine, then I apply inverse sine or arcsine to both sides. So arcsine of theta plus 1 over 2 is phi. That's what I was saying last time. Remember, if you ever have an angle variable on its own, it's going to end up being arcsine of the original one, or arc something, depending on what the substitution is. This is going to be arcsine of theta plus 1 over 2. And there we go. So then we finally finished the problem right here. So this is about as complex as it can get for these trig subs. Not only did we have to do the completing the square in the beginning, but we had to kind of do this little mind bend where we couldn't use our normal variable for this because it was already being used in the problem. So we needed to switch over to a different variable. So this was a pretty confusing one, but we managed to get to the end right here. All right, so there's our example. All right, now what I want you guys to do is I want you guys to try this as well. So Let's go here. I want you guys to do the integral of 1 divided by the square root of x squared plus 2x plus 5 right here. All right, so why don't you guys go ahead and give this a try. And remember, you guys are welcome to work together in the chat. You can ask me questions. You're not on your own with this. So feel free to work with others or ask me, or you could even go online. You could watch a video on this right now or something if you want. Just give this a try, and then we'll, oh, this is practice 2, sorry. Give us a try, and then we'll go over it. I would not crowdsource financial advice. That does not sound like a good idea. Is this practice problem 2? Yes, it is. Yeah, sorry, I wrote P1 by mistake. Okay, this is not Wall Street bets. Don't do that. What should you look for to tell you to use this method? This one's a little bit less obvious. If you have maybe an integral like, I don't know, this, where you have a variable squared plus a number squared, or one of the other 2 situations, that's a good time to use it. Whenever you have a quadratic or something under a square root and the square root's being annoying, that's also a good time to use trig sum, even if it doesn't quite look like what we normally do, because we could complete the square to make it in sum. And Nicola has it right. We're going to use a tangent substitution for this one. Can I explain the arc sine step in the last problem? Yeah, so this was our substitution, right? Theta plus 1 over 2 is sine of phi. So in order to get what phi is, because we need to know for this, I simply took arc sine of both sides. So arc sine of this is arc sine of that. And then arc sine of sine will cancel out the sine, and we'll just have phi right here. We're not doing this example. Yeah, you don't need to use phi. If you're reading like mathematical or physics literature, they probably would have used phi for that. But if you're just doing it on your own, you feel free to use x. But you should be comfortable seeing more than one variable, or sorry, angle variable in problems. Can you use x plus 1 for the x squared plus a squared? Yeah, absolutely. That's what you were supposed to do for this one. How do you find the d theta? Once you make your substitution, take the derivative of both sides of your substitution. What's the integral of secant? Natural log of absolute value of secant plus tangent. I don't often recommend memorizing as a way of studying math, but you should make sure you have like the 6 basic trig integrals memorized. Those are some I would just try to recall off the top of your head. What do we use if theta and phi are used? Oh, that doesn't happen too often. You might use like psi or something like that. Sometimes they use psi, like the trident looking one. That's sometimes a third angle. If you're doing that, though, that's a messy problem. I know most people haven't finished this yet, but for the sake of time, I'm going to go ahead and get started on this in maybe another minute or so. Don't feel discouraged. I know these can take a long time. And don't worry, Kwong, we'll go over this soon. You'll see how to do it. Christian, what's your question?
Sorry, nothing. It just happened for some reason.
Oh, okay. Yeah, there might be some hotkey to raise your hand or something. Can you rewrite a squared plus x squared as a plus x squared? No, because if you FOIL out a plus x, you're going to have a 2ax in the middle. Definitely can't do that. Yeah, powers don't distribute over addition. Is this what's on homework 3? Yes. Problems like this are going to be on homework 3. It's scary at first, but I know you guys can do this. You have to practice it enough, and then you'll eventually get it. All right, let's go over it here. So we're going to do trig sub on this, and I'm inspired to do trig sub on this because I see a quadratic underneath a square root. That's typically a good time to use trig sub. But the problem is I can't use trig sub right now because of this annoying middle term. So the first thing I have to do is complete the square. Complete the square. So we have x squared plus 2x plus 5. All right, well, I don't need to factor anything out of the x squared here, so that's good at least. So I'm going to look for my magic number. That's going to be 2 over 2 squared. I do this number over 2, and then I square it, and that's going to be 1. I have x squared plus 2x plus 1 minus 1, and I have this 5 over here. These guys will factor into x plus 1 squared, and 5 minus 1 is 4. So this is what my completed square looks like. So if I go down this way, my integral can be rewritten as the square root of x plus 1 squared plus 4. Okay, now for this one, I do have something squared plus a number, and there's no pesky middle term anymore. So that's good. So we succeeded at that. Now we have a variable squared and a number squared. So which trig function is that? So we go back to our list up here. When we have that situation, we're going to use tangent. So let's see here. So our variable, or our variable in quotes, the thing involving the variable being squared, is x plus 1. And then the square root of this number is 2. And our chosen trig function is tangent of theta right there. All right, now whenever we do any kind of substitution, we also need to figure out the differentials. So the derivative of x plus 1 is 1, and then we put a dx there. And then the derivative of 2 tangent of theta is 2 secant squared of theta. We put d theta right there. All right, so now that we have that, we're ready to go ahead and turn our integral into a trig integral. All right, let's see here. So we have dx, that's going to give us an extra 2 secant squared. That's going to be on the top here, because the dx is always on the top. Meanwhile, on my bottom, I have the square root, and then x plus 1 squared, well, that's this squared, meaning it's this squared. 4 tangent squared of theta. And then I have plus 4. Okay. Now remember, the whole point of these substitutions, the reason why we go through all this mess is because of the square root here. That's kind of annoying. We're going to turn these two terms, which do not interact nicely with the square root, into one term, which will interact nicely with the square root right here. Why would it be 2 tangent of theta instead of just tangent? I always want to have the square root of this number as a coefficient. Because remember, I'm going to square it again, and I want to be able to match up with this number. Can I explain the denominator again? So x plus 1, remember, x plus 1 is 2 tangent. And if I square that, because I want x plus 1 squared, that means I square this too. And that's going to give me 4 tangent squared down there. All right, now let's get to the main point of all of this. 4 tangent squared plus 4 is equal to what? What's 4 tangent squared plus 4? 4 secant squared. That's right. So here we use the Pythagorean identity connecting tangent to secant. We have 4 secant squared of theta. All right, wonderful. And then now that we've done this, we can't split the square root over 2 terms, but we can easily do the square root of 1 term. So when I do the square root of 4 secant squared, that's going to give me, well, we still have this up here. And then the square root of 4 is 2. Square root of secant squared is secant. All right, and then these 2's will cancel out, and then one of the secants will cancel out from the top. So my integral actually becomes relatively easy. It's just going to be the integral of secant right here. And as I think someone asked this earlier, the integral of secant is the natural log of absolute value of secant. And then now, since we've done away with our integral here, we put in a plus c. All right, so we've done the heavy lifting here. We've done the actual integral part. Now all we need to do is just turn everything back into x's, and then we can call it a day. Unless we're doing Kronos, then we need to type it in. I apologize for that. It is kind of hard to type those in. So anyways, let's figure out how these are going to work. So we have our substitution x plus 1 is 2 tangent of theta right here. How did this get shifted up so much? There we go. We have x plus 1 is 2 tangent of theta, and that's actually pretty nice, because if I just divide this by 2, I know what tangent of theta is. So right away, I immediately know what this is. It's just x plus 1 over 2. All right. Why is there no plus 4 after secant squared? Because 4 tangent squared plus 4 is secant squared. That combined with the 4 turns into 4 secant squared. That's the whole point of doing the substitution, is so we could say that this equals this, and we lose one of the terms. All right. So we know what tangent is, but we need to know what secant is now. So that will require us to make a little triangle. Now, if we remember from trigonometry, tangent is opposite over adjacent. So when we draw our little triangle here, we have x plus 1 as our opposite, 2 is our adjacent, and then I bet you guys could probably guess what's going to happen here. What is our hypotenuse going to be? It's going to be the original integral right there. I see some people talking about the Pythagorean identity. Let's make sure we understand that, because that's the most important part of this procedure here. You need to understand that before we can do anything else. So the Pythagorean identity for tangent and secant is that secant squared of theta is tangent squared of theta plus 1. This is the Pythagorean identity relating secant and tangent here. So this kind of looks similar to this, right? The only difference is that there are 4's in front of everything. So what I'm doing in this problem is I'm just multiplying this by 4. So 4 secant of theta is 4 tangent squared of theta plus 4. And then that's exactly what I'm doing here. I'm taking this on this side and then turning it into the secant squared. And my motivation for doing that is I can't split square roots over addition. This is not equal to 2 tangent plus 2. This is not equal to that. What I'm doing is I'm making this into one term so I can apply the square root to it. That's what's going on here. And this is what we're doing with every single one of these problems. We're using some kind of Pythagorean identity to turn 2 terms into 1. That's what's going on. All right, now back to this. Let's see, how are we doing on time here? Okay, we got about 10 minutes. So if we do the Pythagorean theorem here, we end up getting x plus 1 squared plus 4 quantity squared. And just like all of the other times, this is the thing that showed up in the original integral. Now we're ready to finish this off. Secant of theta is going to be hypotenuse over adjacent. Okay, so our hypotenuse is this square root thing. Then our adjacent is 2. And then we had this from the tangent earlier, and then we have plus c. And there we go. I think this was a practice problem. Yeah, this was practice 2. So if you see this on Canvas, then you can go ahead and put it in there. You could derive a function or take the derivative. Does it mean necessarily that we can integrate it? I challenge you to do the integral of this right here. We could definitely differentiate it because of the chain rule. Try to integrate and see what happens. All right. How many questions are on each exam? There are 30 questions, and all of them are at least as long as this. So, and you have like about an hour. No, I'm just kidding. We're going to make sure you have enough time to finish everything on the exam. All right, I want to do one more example here, and I don't think I have enough. I think I'm going to skip example 3 in the notes. I'm just going to do example 4. And I promised I would put the other notes up the other day. I'm sorry I didn't put that up. I'll put this up and the one I didn't get to do last time here. All right, so example 4, we have the square root of x squared minus 4x minus 5 dx. Okay, so we're going to do this exactly the same way that we've done all these other ones. So what's the first thing we're going to do here? We have this. We're going to complete the square. Complete the square. Okay. Let's see here. So our magic number is -4 over 2 squared. This is 2, and I square it, and I get 4. So I have x squared minus 4x plus 4 minus 4 minus 5 right here. All right. So then I'm going to factor these together. X minus 2 squared. And then I have -4 and -5. It's going to be -9 right here. So this is going to be our completed square. Now we're doing the integral of x minus 2 squared minus 9. Okay, now this one is an x squared minus a squared form. Which trig functions, or which trig function are we going to use here? That's right, we're going to use secant here. And let me kind of rewrite what I wrote earlier when I explained that other problem. Yes, we're going to use x as a secant of theta. Why are we doing this? It's because secant squared of theta minus 1 is tangent squared of theta. So here we're starting off with 2 things, or 2 terms, and we want to get it to be 1 term, because we can't do the square root of 2 terms like this. Do not say it's x minus 2 minus 3, because it is not. We can't do the square root of 2 things, but we could easily do the square root of 1 thing. And that's the motivation for all of this trig sub stuff. All right, so I will use this substitution here. Let's move the integral over here. So let's see. So my variable, my x, is x minus 2. And then the square root of this number is going to be 3. Is there a simpler way of computing these? If there was, I would have told you that way. We're not doing this to make you guys suffer. This is the easiest way to do these integrals right here. So unfortunately, there's not a better way. All right, so x minus 2 is going to be 3 secant of theta. Dx is going to be 3 secant of theta, tangent of theta, d theta, right here. All right, so now that we have all of this stuff, we can go ahead and substitute in here. So I have the square root of x minus 2 squared, so it's going to be 9 secant squared. And then I'm going to subtract 9. And we can't forget about our dx here. I just did forget about our dx. We need to put that in, and that's going to be 3 secant of theta, tangent of theta d theta. Okay, so this is going to be our new integral right here. Now remember, this is the main part of trig sub, so let me ask you guys this. What is this going to turn into? What's the inside of the square root going to go to? I see a bunch of people say it. There we go. It's going to be 9 tangent squared. That's right, because remember, secant squared minus 1 is tangent squared. So if we just put a constant on those, the same constant will be there too. This is the square root of 9 tangent squared of theta. Okay, so then the square root of this, now we can easily do that square root. It's going to be 3 tangent of theta. And then we have this stuff hanging around here. All right. And then if I simplify all of this, this is going to be 9. And then we have secant of theta tangent squared of theta, d theta right here. Okay. So some people are, Logan says, oh no. Why are you saying, oh no? Something not fun's about to happen. So let's look at our powers here, right? So this is going to be a trig integral. So we have yeah, so this one is going to end up being one of those type 3 integrals that we had previously. So this one's the type 3 ones. This is probably the worst trig integral that we can get. Thankfully, this is probably one of the most mild case 3 ones because we only have secant to the first. The way I'm going to do this and the way we do any of those type 3 ones is we turn tangent squared or every tangent into secants. All right, so we turn the tangent squared into this. Okay. And then we're going to multiply this out. And actually, we have some good news for this one. So Nick says, didn't we memorize this? Yeah, so if you took my advice earlier and memorized the integral of secant cubed, we should be able to just do this right away. So remember, the integral of secant cubed is 1/2 secant of theta tangent of theta plus natural log of absolute value of secant plus tangent. And remember, the way to remember that, this is the derivative of secant, and this is the integral of secant. That's what we get for this part. And then we also have minus 9 secant of, oh, oops, no, I'm integrating secant. So the secant integral turned into this, and secant cubed turned into this right here. Can I move the top down for a second? Yeah, there, we can see more of those steps here. I thought it was divided by 2. This part's divided by 2. The integral of secant does not have a 1/2 in it by mistake, or by default, sorry. Okay, so now we've done the integral. We have our plus c in there. That means officially the integral is going to be over now, and we just need to turn everything back into x's. So our original substitution was x minus 2 is 3 secant of theta. And then we have x minus 2 over 3 is secant of theta. So we immediately know what this, and this are. It's going to be x minus 2 over 3. And then all we need to do now is just get tangent from a triangle. Let's see. So secant is hypotenuse over adjacent. Here's our hypotenuse. This is adjacent. And if we do the Pythagorean theorem here, we will get this. And this ends up being the same thing that we had in our original integral. So it's kind of a good way to check your work. Okay, now tangent of theta is opposite over adjacent, meaning we're going to have this divided by 3. Okay, and then we're ready for the monumental task of pumping all of these into these thetas up here. So when all is said and done, when we do this, we have secant of theta times a tangent of theta. And then we have natural log of absolute value of secant of theta. Okay. and then we subtract and we have 9, and then we have natural log of absolute value, and then that's actually the same thing. We could actually simplify this if we wanted to. There we go. So there is our antiderivative right there. So this is kind of another way in which this is kind of the worst it can get, because this was a type 3. I'll just tell you right now, I'm not going to give you a serious type 3 along with a trig substitution. Like this is probably a hard upper limit on how hard the type 3s can get with that. So don't worry. It won't be much worse than this. Now I know this stuff takes a long time. We spent like 15-20 minutes doing that one along with the other ones. And I know there's a lot of steps involved, but the best way to learn this and math in general is to practice. We noticed that we went through the same steps every time. We did completing the square, we picked a substitution, we put it in there, we used the Pythagorean identity, that's the main part of this. We did the trig integral, and then we plug stuff back in. It's the same thing every single time. So the more we kind of just grind through doing these types of integrals, the better we will get at that. So that's my recommendation here. Just keep practicing this until you think, okay, I'm getting this now. I think this is a lot easier than when I started. Where can we find more practice problems? There's a few links to practice problems on the front of Canvas. There's this online textbook that's there, and then there's also a really helpful webpage made by the previous Calc 2 coordinator, Dr. Chui. She's an excellent teacher. She made this really cool webpage with a bunch of worked out problems and examples here. But yeah, so yeah, there is a lot of practice available. And of course, if you feel stuck, feel free to email myself or your TA, and we can help get you unstuck. All right, so that's about we're about out of time here. I'll post the other integral that's part of this worksheet along with the one that we missed last class. I'll post those either later today or early tomorrow here. So you guys can see how those are done as well. But other than that, we're done with trig sub now. So we're done learning this. So we can take a little break from it, and we're going to learn another technique on Friday here. So I will see you guys then on Friday. Although I do have a few minutes now if you guys want me to ask like a quick question or something. See you guys on Friday in person, hopefully. Samuel, do you have a question?
No, I just wanted to say thank you.
Oh, yeah, no problem. Can we see the cats? Let me answer some people's questions here real quick, and then if you stick around, you can see the cats. I showed the first practice problem. Yeah, that was just completing the square. You end up getting this. Is crying allowed on the exam? Please, I don't know. You guys will do all right. Like I was saying, if you practice enough, I'm not kidding, you guys can do really well on this, even with trig sub. Can you read the steps that he said are all the same? Yeah, we complete the square, we pick a trig substitution, we substitute that into the integral like we make it with thetas, then we use the Pythagorean theorem, the identity, to get rid of the square root, then we do the trig integral, and then finally we plug back in x's. How many do you recommend we practice? I recommend that you practice enough until these start to feel easy. Once you kind of start getting bored of this, not because it's hard and you want to zone out, but because, yeah, I already know what I'm doing with this, then you've probably practiced enough. So however long it takes you to get there, that's how long I would practice. And for some of these, it might be just you do a few of them and then that's it, because you instantly got it. But in some of these, you may need to practice a bit more. All right, yeah, let me show you guys the cats here. Let's see if they're still taking a nap in here. Oh, they're spooning now. Here they are. We love babies. Yeah, he's got his leg on him. Oh, cleaning time. Oh, Merlin's embarrassed. All right. How do you memorize the integral of secant cubed? Yeah, it's just like Cynthia said. It's half the derivative of secant plus the integral of secant. All right. Well, that's all the time I have for now. So if you have any other questions, feel free to email me and I will see you all on